I am. And for those who just came in, there's the link to repo, which has the slides and all the notebooks. And you can also find it if you go to GitHub and you go to Aki Vehtari, and then one of my repos is called now Model Selection Tutorial. And there's 4 notebooks I'm going to use. And if you go to that GitHub page, it has also links to HTML versions of those notebooks so that you don't need to run R, but you can probably follow easier or look at the kind of the things. Maybe I go too fast sometimes. Yeah? So now today I have only a little about the basics of predictive performance estimation, but you have at least now a good background, everyone, with the basics of STAN and making these predictive models. I do talk a lot about cross-validation, and I often recommend using cross-validation, but then I also start in the beginning showing an example where we don't need cross-validation, and it's I can show also that the cross-validation is actually there, even kind of the weaker choice than just looking at the model posterior. And then examples where cross-validation is useful, on accuracy of cross-validation, cross-validation hierarchical models, and when cross-validation is not enough, which is the case of very large number of models. And then there's a little bit about forthcoming LU version 2. Should be hopefully in a few weeks in CRAN. And then just one slide about information criteria. So WAIC, it's asymptotically equal to Bayesian leave-on out. And so some of the discussion holds for WAIC too, but it doesn't have as good diagnostics and fails earlier than the Pareto-smoothed importance sampling LU used in LU packets. So that's why I don't then spend time on WAIC. And for kind of the background on theory of why I think the SysLU is better is here. It seems I was updating the slides on the plane, so the archive numbers are missing there, but I'll add them after talk. So we have now here the model. So we have the model prediction for a future observation. Observation is Y, and then we put a tilde over there to be the future observation, what we're predicting. We have observed data, and we condition on now some model K, so we can have different models. Now when we do these predictions, we could then evaluate the predictions we make and these predictive distributions in several ways. But I start now with using just the log score, which is now the information theoretically justified way if we want to estimate the goodness of the whole distribution. So we have here the predictive density. We take logarithm of that. We evaluate it with some future observation Y tilde, but we haven't seen the future yet. Ideally, we would know also the future data distribution, and then we could average over the future data distribution, and we would know then what would be the expected log predictive density, and that would be our measure how good our predictive distribution is from model MK. But now the problem is that we don't know yet these future observations. And we don't know this true future distribution. Following Bernardo and Smith, there are three different approaches then dealing with this unknown PT, M-open, M-closed, and M-completed. And today I talk about this M-open and M-completed. So in M-open, we avoid explicit specification of this PT by reusing the observed data as a pseudo Monte Carlo samples from the distribution of future data. And one example of that is the Bayesian leave-one-out cross-validation. So we plug in already observed xi and yi in the predictive density, and then take average over all those, but just to correct that we don't use observations twice. When we condition for yi and xi, we remove them from data when we fit, and when we fit the posterior distribution. And you can now now we are evaluating then the predictive distribution with only n observations from the future data or n pseudo observations from the future data. This is almost unbiased estimate for single model. And then naive computation would require then computation of n posteriors, so that we would need to condition on all different data sets where we've left out one observation. Generally, there are, for some simple models like Gaussian linear models, there are analytic solutions. For some models like Gaussian latent variable models, Gaussian processes, there are good analytic approximations. Stan uses impedance sampling, I explain soon. And then we can also do k-fold cross-validation, where we just reduce the number of posterior refits we do. So when we do the leave-one-out, so now I also saw here's the leave-one-out predictive distribution, but we can divide it so that here we have the prediction given theta, and on the other hand we have the theta's posterior given the leave-one-out data. And now the leave-one-out posterior is close to full posterior. And then we can take that benefit from that it's close to full posterior, and use the impedance sampling. So in impedance sampling, we draw the samples from the full posterior, and that's what we do with the Stan easily. And then we can use this impedance weighting equation here, so that instead of when we compute expectations using these posterior draws, we weight these draws with this W weight. So the I index is that it's for each leave-on out posterior, and S is now the draw number of the index for the draws from the posterior. And so the importance weight is so that here we have the density from the full posterior, here's the density from the leave-on out posterior. So if the leave-on out posterior density is somewhere higher than the full density, we get the weight, larger weight, and if this is somewhere lower density than this one, then this gets smaller weight. Now, these terms directly include the normalization term. But it now turns out that we don't need to know the normalization terms, which we don't have easily, but the weight is proportional to this term, which is just 1 per 1 likelihood term. So this is the likelihood term yi given 1 draw from the posterior. And these are easy then to compute, and since we are using the self-normalized version, so the term under the line there makes the self-normalization part, and we don't need to know, or it's enough that we know that the proportional weight. So this is enough what we need to have. And here's an example for StanCon. This is really simple Bernoulli model. If you look at the model block first, the last line of the model block is y is distributed as Bernoulli logit and eta parameter, and then in generated quantities we can compute. We need to do this in loops because these LPDFs and LPMFs don't support. So if you give a vector of observations, it sums the log densities, so we need to loop over to get these individual values. And now in a usual way, instead of computing the density or the likelihood directly, it's the log likelihood terms there. We can then use. Additional thing made in loop package is using the Pareto smoothing and the Pareto diagnostics. So we have the importance weighted expectations there, but now it's possible that these importance weights have really high variation. And if they have a high variation, it's possible that one of the weights is really, really large, and then it dominates, and only that draw would matter in that equation. And then there's two things. So we have this Pareto diagnostic looks at the shape of this weight distribution and can then infer how good estimates we can assume to get from the importance sampling. And on the other hand, it is also possible then to change these weights a little bit, smooth them, reduce the variance of the weights a little bit, which gives us additional benefit. So there's the quick summary of, but I'll come back to the K values in these demos. So the loop package in Gran implements Sysloo, and there's also for Python users, there's this Sysloo functions available. There's now also difference that the current Loo version is using the older version of this Pareto smoothing, and then there's in the autumn new version came out and then the loop 2 will have that new improved version. I'll show also some additional diagnostics we now get in loop 2. RStanArm has integrated support so that you don't need to write these locally in generated quantities, and then it can get a lot of things more easily because we know more about the models. And there are the references for this. Overall, the idea, why we did this loop, we don't claim that this would be always the best thing to do. It's just something that after we've done the sampling from the full data posterior, it's so easy and so fast to compute, and since we have the reliable diagnostics, it's something that you get practically free, and in many cases it is helpful. But it's not something that would then always be right thing to do. And we can do also model comparison. So when we have two different models, we compute these expected log predictive densities for each observation, and then we can compute the difference. And now it's important that we do the pairwise difference, especially when we compute then uncertainty for this. So the uncertainty shown in this loop package output, it now comes from that, since this was our kind of pseudo Monte Carlo estimate to integrate over the unknown future data distribution, in the same way when we then do the empirical average, we can compute the standard error for that empirical average estimate. And that's also then where kind of the weakness of cross-validation comes, that since we have the only n observations from some distribution, we will have additional uncertainty about in the future. Okay, now I go to a notebook, beta blockers. It's an example where we can look at the posterior directly. We don't need cross-validation. So this is comparison of two groups with binomial model. Now I think you don't, which point you can see the text? So can you see at the back? Yeah, at least someone can see, someone with the supervision. So there was a beta blocker medicine, and out of 674 patients receiving the control, 39 died. Out of 680 receiving the treatment, 22 died. And then we want to ask, is this treatment beneficial? We put the data in. With RStanArm, we can easily then fit using Stan, GLM. Now the y divided per n is, and then this is now just one variable, the group variable, and so it's like the latent linear model where it's only the one group variable telling, and then automatically it adds also the intercept term. And then we have also the weights here to complete. We can sample, and then we computed here odds ratio. Now I need to make this smaller to get the bigger fit. odds ratio, automatic tick labels doesn't seem to work so well. So 1 would be here. So odds ratio below 1 would mean that the treatment helps. And then if we compute how much mass there is above 1, it's just 1%. So we have 99% probability that the treatment helps. So now we would not need to do any cross-validation if we trust the model. That's fine. We can just look at the posterior distribution and make inference based on that. Now I saw what happens then if we still use cross-validation. So you can see also the weakness of the cross-validation. So now the previous model had in RStan-ARM, this binomial model, it had only 2 observations because we aggregated the data from one group and the other group, and now it doesn't make sense that we would do leave one out by leaving one group and trying to do the inference only with the control or only with the treatment. So I changed now the model so that I have now individual data, and for each individual in which group they belong and whether they survived or not. And so here's the alternative model. So StanGLM, Y, again, it depends on group parameter. It's a binomial, but now the data was different, so I'm replicating here making the arrays of. So the target Y is 1 for all who died and 0 for all who survived. Now we can then, the usual thing then people do would be then have also the null model, the model without coverage. And so in this case, the coverage was only the group parameter. And then here's the null model where we have just only the intercept term. And we can then use cross-validation to compare these models. So here you can see now we call loop function, give the fit there, and it gives us the expected log predictive density, estimate for that, standard error for that. It tells estimated effective number of parameters. And I don't really like this, but then some people like to multiply log densities by -2 due to historical reasons. And then the important thing is this, all Pareto K estimates are good, K below 0.5. This is something you need to look at, and I'll have also examples where that doesn't hold, and then talk about this case more. And then we have the null model. We get something out, but now we can't compare these directly looking at these numbers. We need to use the compare function so that it does the pairwise comparison so that we get the standard error correct. You can see that for model had the group parameter, standard error is 23. For null model, 23. But when we do the difference, the standard error is much smaller because both models, they are making a little bit similar predictions anyway. In this case, why they are making a little bit similar predictions is just because in both groups, there was quite small proportion of these patients who died, and then it's in a way that even if you predict with the average probability, you will get this certain kind of the guess that what's the probability of someone dying. Okay, now we see here the difference in expected log predictive density, and if we compare it to the standard error, we see that, okay, there's not much difference. But we did see, anyway, from the posterior, we saw already that it was 99% probability that treatment helps. And now this is just the weakness of cross-validation, that when the effects are weak, the additional uncertainty in a cross-validation, so the posterior was using model, cross-validation is using the model, but also it's using this non-model based approximation for what's happening in the future, and that part is giving us the additional uncertainty. We can also think that, putting this in perspective, so that we had 674 in one group, 680 in other group, and the percentage of deaths were 5.8 and 3.2%. If you know about the usual accuracy of like political polls, you know that we are actually in a weak data area still. So that also explains why cross-validation is not so working so well here. I've added also simulation experiments showing a little bit more about this, that this one is now showing, so the y-axis is there are odds ratios. The first one is odds ratio 1, and then odds ratio 0.1. And then with each odds ratio, I simulated data, 1,000 simulations, and from each simulation, I simulated data, I fitted a model, and then I looked at the posterior distribution and what was the probability that in the posterior we would see that odds ratio is below 1. So when the odds ratio, true odds ratio is 1, we see that what we should expect also, that there's uniform distribution for these probabilities, that our estimated odds ratio is below 1. When the true odds ratio gets smaller and smaller, it's more and more likely that we see the effect. And around here, we'll then, most of the time, see the effect. Now we can compare this, what happens if we would do cross-validation and comparing to null model. We see that we need more informative data before we would almost every time say that, okay, there's a difference between these models. Now, this is not the, now the additional uncertainty was then, again, it's because of the cross-validation doesn't make any model assumptions for the future. We can also, this is something which is close to cross-validation in that way that we are looking at the predictive performance, but now we are using some model for the future data distribution. And we can see that using a model for the future data distribution gets back the similar kind of performance for seeing the effect as if we look at the posterior. Okay, back to slides. And now the M-completed version. So now we replace the unknown PT with some reference model. And now this reference model, we have then a distribution for Y, and then we can integrate over that, and we can get better accuracy from that. In this beta blockers example, the reference model was now the model with the group variable, so it worked because, again, it was a so simple model. We could trust that model. In my simulation, it was actually the true model. It may introduce bias if it's not good enough, that reference model. But again, the unbiasedness is not the primary goal. We prefer to get smaller error in any estimate. But when using these reference predictor approaches, we have to be careful. And that's why, again, the cross-validation is a good default choice because it doesn't make so many assumptions. And I'll come back later to these reference predictive approaches when we have large set of models and we really need these smaller variance in estimates. Yes? Yes? Yeah, so this is the one you specifically trust. And these are, MKs are then bunch of models you don't necessarily trust. For example, we would always trust the more complex and richer model should be usually better, taking into account more uncertainties, but then we might know that can we instead use simpler model? Okay, examples where cross-validation is useful. Treatment effect on number of roaches. So this is from Gelman et al., and this is also a notebook by Jonah Cabri, Ben Goodrich. Or the data is taken from there, and then this notebook is for the model selection part. So there's treatment and control applied to 160 and 104 apartments to test pest management system for reducing the number of roaches in urban apartments. And so there were set of traps in each apartment, and different apartments had traps for different numbers of days and so on. So I just noticed there was some, I need to pick some of the equations still there. So we get, the data is in RStan-ARM packages, so data roaches will fit Stan GLM model. And so the important part here is that we are using now Poisson model for the number of roaches. And here's the model, so that we assume that number of roaches depends on number of roaches seen before treatment, whether the treatment was given or not, and the senior coverage is whether this building was specifically senior people building. And we fit the model, and we can look at then marginal posterior. So there's the intercept, rows is before, treatment, senior, and now it might be difficult to see. Here's 0. So everything is now clearly away from 0, and so there's a treatment effect and senior effect. But let's see what happens with the cross-validation then. So we call Loo, we get here the ELPDs, number of parameters, and so on. Now we also get something for the Pareto K diagnostics. And if we have values, K values, which are below half, we say they are good. Most of them are good. If we have from 0.5 to 0.7, they are okay. But we know that the accuracy or effective sample size starts to decrease, and that's what we add also to Loo 2. But then these bad and very bad, now it means that we should not trust these low values. Now the full posterior and leave-one-out posterior are so different from each other that the importance sampling failed. It means then that these specific observations are highly influential, which is also an indication that there might be something wrong with our model. In many, many cases, when you see really high K values, you know that your model is not robust enough and can't explain some of the observations well at all. I come back later what to do when we see these high k-hat values. In initial, when you're exploring, you don't need to rerun with the more computational intensive approaches. If you have just few, like here there's 6.5% are bad and very bad, it's enough for us to see that there's something wrong, and it's also enough to see the later differences. But for if you would choose a model that would be your final choice, and if for final model choice you would still have large K values, then you would need to do additional computation. We can also easily plot these K values, and we've added the lines so that, okay, these are the good ones, these are the okay ones, bad, very bad, and then it would be possible also to show, instead of pluses, so the actual the observation number, and so you could go also to the data and check that, okay, what's wrong with this data. Ben has told that he's seen many cases where these k-hat values also revealed that there wasn't a problem with the model, but there was a problem with data. Okay, now we can do cross-validation comparison for covariates, so that I form now 3 models by dropping each of the covariates out at a time. So I get, so here's M1 refers that it's minus the first, so roads 1, and the others, treatment and senior, are still there. Here this one is missing then the treatment, and this one is then missing the senior. And then by comparing to these models to full model, we could see that how much our predictive performance drops if we remove some of these variables. And now when we compare, so if we drop the roads one, we see that, okay, the difference in ELPD diff is significant compared to the standard error. But if we drop out treatment, the cross-validation doesn't see the benefit from significant benefit or from the senior. So now there's also, of course, we could assume that maybe the cross-validation is again weak detecting these effects. But these were not weak effects. If we look at the posterior, they were far, far away from 0. These were really far away from 0. So there's also now reason to suspect our posterior distribution if the cross-validation can't detect that removing these would be useful. Reason why cross-validation and posterior distribution disagree is that we have a model misspecification. We can suspect the model misspecification because of the k-hat values also. And we can also then use posterior predictive checking using the base plot package, where we've now plotted the proportion of 0 observations we've truly observed and proportion of zeros we get if we generate replicate data using our model. Yeah, so our model is just rubbish. And here the cross-validation was helpful in 2 ways, both in the k-diagnostics and then in comparison. Okay, next we fit negative binomial model. It should be more robust. And then we look at the posterior distribution for the negative binomial model. Here's 0, and the senior effect, it has gone away. Treatment effect, it's weak. It is again, quite high probability that there's a treatment effect, but much weaker than previously. We can look at also these pairwise joint posterior plots. I'll come back later to more interesting examples, but now you can kind of remember that these were kind of okay. And then we can compute the loop again, and here Pareto K diagnostics. There's now there's now only one bad values. There's still one which is difficult, but also the K estimate has some variance, so it is possible that also this bad between 0.7 and 1 is just by bad luck of when we are drawing from the posterior, and just drawing more posterior draws could also get rid of that bad K value there. And we can compare the Poisson model and the negative binomial model, and the difference is large compared to uncertainty in the comparison. We could have also, we could see that this negative binomial model is better than Poisson by looking at this extra parameter in negative binomial model, which describes the overdispersion compared to Poisson. And since it's small, we know from that Poisson can't be a good fit. Or we can use also these posterior predictive checks. And now our replicates distribute nicely around what we truly see, the number of zeros. So the model is much better. And then we can do again the variable comparison, that what if we drop out each of the variables. Now we still see the previous number of approaches is important. It's uncertain about whether there's a treatment effect. It's uncertain whether there's the senior effect. But then again, from the posterior distribution, we could see. So the cross-validation was helpful here, not just in the looking at which variables have meaningful effect, but also noticing the model misspecification. Another case is that even if we don't have model misspecification, complex model, there can be posterior dependencies, and it can be difficult to analyze the posterior. So we look at the collinearity in coverage. So last year, I happened to see this Andrew Tyer's blog post, Does Model Averaging Make Sense?, where he was using AIC and stepwise regression and things like that, and I wanted to make a Bayesian version of that. And the good thing was that Andrew Tyer's notebook included nice data, collinear data. It was something to do with some birds and the living environment coverage. Important part is that if we look at these pairwise plots of the coverage, we see there's correlations there. And then we fit Poisson model, so there was a number of birds, so that there was Poisson model, and then there was these 4 coverage, x1, x2, x3, x4. And we can look at the values, and this also demonstrates that actually if we switch to QR transformation, we get faster inference and so on. And actually, in the future, you will see something larger than 4,000 here in NFs. So we get super efficient antithetic sampling there. So anyway, after we fitted the model, it's fitting nicely, converged diagnostics, doesn't reveal anything problematic. And we can then look at the marginal distribution. So it's common to look at these covariate effects as marginal distributions, and now we would say that, okay, none of the covariates are meaningful, the marginal distributions are overlapping 0, so clearly we don't know whether they are any use there. But don't give up. You can look at the joint distribution. And we see in the joint distribution high correlations. And if we zoom to one of those, so this is x1 and x2, joint distribution is not overlapping 0. So they are highly the relevant variables. It's just that if we look at the marginals, we didn't see anything useful. In this case, it was easy with just 4 covariates to look at these joint distributions. But more and more covariates we have, more difficult it is to see. It might be that it's not enough to plot anymore pairwise. We might need to look at 3 variables at the same time, and then it's difficult to see in 3 dimensions whether 0 is outside of the highest density region or typical set. So we can do then cross-validation, leave one out. We do a null model. So now the null model doesn't have any variables. And then we can compare, here's the comparison of the null model and the model with all the variables. And we see clear difference. So we can say, yes, these 4 variables contain some useful information, even if the marginals are overlapping 0. And in this case, we were also able to see that if we look at the pairwise, we can see something. On accuracy of cross-validation, so I've been pointing out that we have the ELPD diff, and we have the SE, the standard error, for that. Now, we can't use those to give exact probability that one model would be better than other. We know that because of the dependency in a cross-validation that we are in a way there still using, even if we avoid, in the expectation we avoid the double use of the data, the reuse of the data in the cross-validation, it still leaks in this variance estimate, and then because of that to the standard error estimate, it's slightly underestimated. We could correct that, make some corrections on that. It's also that the difference distribution, or and also the ELPD distribution, ELP distribution especially is usually highly skewed. Also, when we do the pairwise comparison, that difference distribution is likely to be skewed, not necessarily. And so currently we just recommend that, okay, you can look at this kind of compare the ELPD, that is it much larger than like twice the SE, but we don't recommend that you would compute some exact probability report in papers. We know how to slightly improve the calibration of this, and we'll report results hopefully later this year and better recommendations on what to exactly report. But it's anyway useful to look at these diff and SE values. Okay, when we have high k-hat values, in our paper we denoted this as a Psislu plus, and we can compute leave and out posterior exactly for those observations for which k-hat is larger than 0.7, because quite often there was only a small portion of k-hats which were large, so we already get this big speed improvement using the impedance sampling for all those where it's easy, and those rest of we can just refit. So if your model doesn't take too much time to refit, you can add the additional option there, and then for R-stan-R models, the loop package does things automatically. Another option is then that instead of leaving one observation out, leave a block of observations out. And when we divide the data in k-blocks, it's called k-fold cross-validation. And if we choose, for example, k10, it means that we need to do only 10 times additional computation as for our full posterior. And it's still, we are using 90% of the data to fit its cross-validation posterior. So we should get similar posteriors as with the full data quite often. And in R-stan-ARM, it's possible then to run k-fold. And we can also use the k-fold C. If we have a hierarchical models, I'll say something more about that. So there's two different possibilities for hierarchical models. Predicting new WAICs given all the existing groups. So for like for the treatment effects, if we would have different hospitals, we could think about then predicting the treatment effect in each hospital, but then thinking that what if in these same hospitals we get a new patient. So we can leave out one patient in one hospital and then to do the fits. Or if we are using k-fold CV, we just randomly leave patients out from all the hospitals. So 10% of the patients from each hospital is left out. And that's good if we want to know, predict new Y given existing group. But then we might be also interested in predicting that what if this treatment is taken into use in a new hospital? And then what we would like to know is that, how we can do this in a cross-validation, simulate this kind of case, is that we would leave all the patients from one hospital out, fit the model, and then predict to those. And in this case, it is also in a way that here we have more of the focus on a lower level, here we have more of the focus on population distribution for thetas. And Loo version 2 will have some helper functions then to do these grouped k-fold CV things. Okay, why don't we use importance sampling if we leave one group completely out? It's likely that when we leave many observations away, that the bunch of observations together is more influential and it's changing the posterior distribution too much and importance sampling fails. But then it's possible, it would be possible to do importance sampling style using marginalization in style what the Rave Hesketh and Poor talked on Wednesday morning. And okay, now this requires then some separate software, but maybe we have also in something related to this in Stan, ARM, and Loo later. If we do this, the first case, predicting for new yi, and so we randomly do these things. Yes, 2014 paper showing that simulated example where having a hierarchical model and the x-axis is sample size, so we get more and more data in each group. When there's not much data in groups, the complete pooling is close to hierarchical model performance. No pooling is really bad if we don't have much observations per group. But when we get more and more observations per group, eventually we don't need pooling at all, or the no pooling model and hierarchical model give the same performance. Complete pooling gets worse. But you can see that in these kind of cases, the cross-validation can be that in a way that eventually the differences are small, and it's not, if you have enough data in your groups, you are not able to see the difference. But if you would then leave the whole group out, you would see something different, as also was in the Wednesday, shown in Wednesday talk. We are adding to the loop package so that we get better support for hierarchical model cross-validation, and adding also then examples. Okay, I seem to be running out of time. No, not yet buzzing. So when we have large number of models, we have a problem that if we use cross-validation to do model selection, even if the cross-validation for single model was unbiased, the selection process itself is going to fit more to the data, and we are going to overfit. And this was recognized already, for example, Stone, 1974, but it's often forgotten. We could use two-level cross-validation to estimate then the performance of the selection process itself, but it doesn't help choosing better models. And bigger problem with coverage selection. These are toy examples in coverage selection. So we have 20 observations, 50 observations, 100 observations. I'll just continue. X-axis here is number of coverage in the model. So the full model would have 50 coverage. Dashed line is the performance of the full model using some good prior. And blue dashed dot line is that we start from the 50 coverage and use cross-validation to choose which covariate to remove. Get 49 coverage. Then use again cross-validation to choose which covariate to remove, and so on. And you can see that that blue dash dot line is going up. It's the cross-validation thinks that it's finding better models than the full model. And the black line is then, if we compare to independent test data, and we see that actually we are finding worse models. So we have the problem here that we are fitting the data. And I have another 10 minutes. Okay. Okay. So here, another simulated data. The first line, cross-validation. Second line, WAIC, DIC. And we can see that they all perform similarly, really bad. So there was 100 coverage, 100 observations. Then we get second column 200 observations, fourth column 400 observations. You can see now that the red line is how the cross-validation thinks how good the model is, and the black line was the true performance. They are getting closer. So if we have lots of data, we are fine using cross-validation, also selecting from large number of models. But if we don't have much data, and I was yesterday talking about these small n, large p cases, and then in those cases, we know then that if we would do variable selection with cross-validation, it doesn't work. These are marginal posterior probabilities, so what you would get, for example, running spike and slab model and looking at the probability that you are in a spike. This one is now the reference predictive model, where we use the reference model is the Bayesian model average, so it's the kind of the full model integrating over all possible variable combinations. We see that it's performing, if you look at the black line, that's the important thing. It's much better than cross-validation, so using reference model helps. But this is the best one, the projection predictive approach. You want to?
Yeah, I just want to do a quick announcement. You keep going, okay? So checkout, the technical checkout is your key stops working at noon. Like as in, to get into your room, you're going to have to go to reception and figure out a way to get into your room. So there's no flexibility on that, all right? So I suggest you, in this time period, sneak out, handle your room, or and come back, or just figure it out. But you gotta be out of there by noon. All right. You don't have to go to reception to check out. There's no formal process. Just leave your key in your room or whatever. Okay. There's still stickers in the back and a survey in the back, and we are going to put T-shirts up. If you want more than one T-shirt, go back and get it. If you don't have a T-shirt, get up there now, and you want to get it. And then speaker catchers. Please get your speakers lined up for after Aki, because we're going to go, depending on how long you go, we're going to go straight to Susan.
10 minutes.
10 minutes? Okay, so there'll be a very small break. But 10:40, we got to be here and hitting the road because we want to get lunch at 12:30. And lunch tickets still work, okay? So if you want to go and run around and do things, please be very quiet as you slip out of here as you demoralize Aki. And then please continue. Thank you.
Sorry, I have so much to say.
Yeah, quiet, no talking. Seriously, no talking. Who is talking? Out. If you're going to go outside. All right, great. Aki, please keep going.
Okay, so here are the averages from several repeated simulations, and here you can see the gray lines are the individual lines, and you can see again with the cross-validation and WAIC, there's much more variation in this model selection, and then the reference model was already much better, but then the projection is even better. And I try to squeeze this in 10 minutes, this projection. The approach we have implemented in ProjSpread package, it's based on the papers Dupuy Robert, but this decision theoretic idea of using the full model and then thinking that how to do the inference if in the future you are allowed to use only some of the coverage, it dates back to Lindley in 1968, and it's strange that it's not used more. I don't understand why people want to be so much doing Bayes factors. And so it performs well in practice. So there's the paper, and you could already see some of the results. Has low variance, able to preserve information from the full model. So the general idea is that we need to start with the full model with all the variables. And if we have a lot of variables, then Horseshoe is, for example, useful to make this full model and still include the information that only a small number of things are relevant. But as I yesterday showed, the posterior with Horseshoe, it still has some uncertainty around the zero. If we have a lot of these small uncertainties around the zero, so it wouldn't matter if we would remove small uncertainty, just one piece, but if we remove lots and lots of small pieces of uncertainty, they accumulate to be a lot. And so we take the full model, and instead of the reduced with the reduced number of coverage fitting again a posterior, we project the full posterior to subspace, restricted subspace, and this projection is made so that we minimize the Kullback-Leibler divergence of our predictions. So we take the full posterior, and then how we can project it to a restricted subspace where some of the coefficients are zero, so that our predictive distribution would stay as similar as possible. And then for a given number of variables, we choose the model which has the minimal projection discrepancy. You can do backward, forward, you can do other things. Yeah, just a moment. So in those figures, they were backward. I'll show you the forward, and I'm afraid I don't have time to go other advanced approaches to do the model search path. So here's our full model predictive distribution. And then the question was, what's the best Q projection distribution given the constraint? And so that this is obtained by integrating over the full posterior. This is obtained by integrating over the Q, which has the constraint that some of the thetas have to be zero, but then we want to choose the Q so that still for those non-zero thetas, this distribution is such that the scale divergence is then minimized. And we can do that, so to make it quick, we
changed a little bit of order of integration and optimization, and we do it by draw. And now I'll skip this. But say that, okay, this projection for Gaussian case, we can get analytic solution, how to get each draw from the full posterior project to a draw in a projected space with these equations. And you can see it's also projecting in additional weights, the variance. And for exponential family case, it's equivalent to finding the maximum likelihood parameters for the submodel with the observations replaced by the fit of reference model. And these are fast to make. Here's an example having the full model and then the projected model. And now the project model has the variables ordered in relevance. So it's not feasible usually to go through all possible combinations. Of course, if we have small number, then we would go. And then that's why we would use, most often we would use forward selection, just because if we assume that there's only small number of relevant variables, we can stop the forward selection early in a way that as soon as we get a good performance, we stop. The broad spread package also has a faster way than the forward search. So when we have a very large number of models, we can get a quite good guess for the order with L1 norm search. But we will describe that. So it's not yet even in any paper, the description of this faster approach. Just reminding about the good results, and then also now comparing to lasso. So this is simulated example N80, 200 coverage, only 7 are relevant. This is the lasso path, mean square error, and this would be the cross-validation based selection what would be the GLMnet package would choose. So it would choose more than 40 variables on average. And also then you can see how the path goes, so that it goes slightly lower, but it's not easy with the lasso to find the smaller models. And then here's the full model base with horseshoe prior, beats lasso, and then this projected projection predictive approach path. You can see that we can get to much smaller models and maintaining the accuracy. The small difference here that this is going just below the full model, it's again just because of the noise. But in practice, we can really find, and this is then when we have the stopping rule on average, it stops things that, okay, this is the amount of variables which is good to choose, so much less. You can get sparser results. And finally, quickly, this last notebook. In that specific simulation, I don't remember which one. But of course, we recommend using the regularized horseshoe all the time now, and we might sometimes even say horseshoe even if we used regularized horseshoe. Oh, I forgot. I had the also for the collinear example in the end. Here, how it looks like. So we are doing forward selection. So you see the collinear example, 0 difference to full model, 1 parameter added, the best parameter added, difference to the full model, 2 variables added, and now it's as good as the full model. And we can get the projected posterior. And the projected posterior looks nice. We have here 0. And then, since this was simulated data, the true values were, let me see, I had them somewhere here. Okay, now I can't, but these are actually, the true values are inside all these marginals very nicely. So it was even able to recover quite well the true values and those variables which contained most of the information. And the diabetes example is another one. This is the Pima Indians diabetes. You would see marginal like that, and then you would want to know that, okay, which coverage I want to use in the future. And then you would do the projection. This has also other nice cross-validation related things. So using horseshoe, and then we see there's correlations, and then order, again, the proj spread gives us that, okay, 4 variables gives as good performance as all the variables, and then we can do also the projected, okay, just 3 was enough, yeah, 3, and we get the projected posterior. And it would be then in the future, we would know that, okay, it's enough to measure these things. So now, useful in medical cases, we can reduce the number of observations we need to make in the future, number of measurements. And okay, so this is not yet in CRAN, but it's in GitHub, and these notebooks had a code how it installs automatically on GitHub. Lu2, I already mentioned, there's going to be the improved Pareto smoothing. There's going to be also model averaging, pseudo BMA plus weights, stacking weights, helper functions for k-fold CV, and that's it. And there's references in the end for all the material. That's it.